we shall now talk about the system design issues involved in cellular systems. First, the basic concepts involved in a cellular system design. The basic requirement is of high capacity. High capacity is achieved by limiting the coverage of each base station to a small geographic region called a cell. This is different from the traditional radio transmitters which would cover the entire city and the whole city was one cell. This is a paradigm shift. In order to achieve higher capacity, that is to support a larger number of users, the city first must be divided into smaller cells and each cell must have a transmitting tower called the base station. The same frequencies or time slots or codes are reused by spatially separating the base stations. So, this factor of being able to reuse the frequencies actually allows you this high capacity. That means a larger number of customers, more revenue, sustainability of the system. However, the moment we put more number of cells and at the same time promise the customers that they can move around because it is a mobile situation, we should have a mechanism to hand off the calls from one cell to another. So, this is the price we have to pay in order to give enough mobility. This approach resolves the problem of limited radio spectrum. If we had the luxury of using infinite bandwidth, we do not need to reuse. Otherwise, we will have to resort to the techniques of frequency reuse. Let us look at some more basic concepts. The neighboring base stations are assigned a different group of channels so as to minimize the interference. What do we mean by channels? As we saw earlier, we have certain frequencies or time slots or codes and they form the channels. Since we have differentiated the entire regions and divided it into subcells, the neighboring cells must not use the same resources. But then we have to reuse it after some time. So, we have to come up with this notion of reuse distance and frequency reuse planning. If we do not plan well, we will at the end of the day increase the overall interference. Interference will be an issue. We will also see certain mobile systems are interference limited. By systematically spacing base stations and the channel groups, we may reuse the resources as mentioned before, and as demand increases, the number of base stations may be increased, thereby providing additional capacity. So, there are ways and means today to expand your services. If your number of customers increases, you can scale up your system. So, this reuse factor and certain other advanced techniques will allow you to continue providing service to more and more number of stations, even though you are not asking for extra bandwidth. This is a basic concept. All right. A very intuitive understanding is as follows. Just like the whole city has been divided into cell, each cell can be divided into subcells and further and further. So, use smaller and smaller subcells within the cell, but keep in mind that the cell size can be reduced only if you reduce the power. Actually, what determines the cell size? What determines the cell shape? We will discuss all these things, but clearly the transmitted power is a factor which will decide how big your cell is. So, I can reuse and include more number of users provided I keep my emitted power under control. Now, let us gradually build up and understand how a cellular network is laid out. Suppose I have a base station here shown by a tower. There is transmitting antennas at the top and a transmitting unit maybe at the bottom or at the top. It has a region of coverage. Here I have shown it as a hexagon. We will discuss why hexagons are traditionally used, though in reality the real base, the cell shapes have nothing to do with the hexagon. It is a concept which we will discuss. So, every cell has a base station. Suppose we would like to provide coverage to an area, maybe city X, using these cells. Now, I would like to put more number of cells to cover the region of coverage. So, I have several cells. Here, for the sake of simplicity alone, I have shown all cell sizes to be equal. Within the same geographical location, most likely all cells will not be of the same size. In fact, the terrain, the blockage, the density of people, traffic, all will determine how big or small the cells would be. For example, in Delhi, the cells near the Connaught Place area, which has high urban density, will be much smaller. The cell sizes will be much smaller, and hence which will provide higher capacity. So, cell size can be made smaller to do a higher degree of reuse and hence provide much higher capacity. In outskirts of Delhi, where the density of mobile phones is not so high, we will have larger cells. So, the entire city has been subdivided into cells with each base station put at the center of the cell. Now, somehow these base stations need to communicate with each other and also to the external world, because the mobile system does not stand alone. It has to talk to the public switched telephone networks, because I should be able to make a call from my mobile phone to a landline phone and vice versa. So, the brain behind the cellular system lies in this MSC, or the mobile switching center. Clearly, if I have to coordinate the activities of various cells, I need to put a line to all the base stations and connect them to the mobile switching center. So, let us do that. So, every base station is actually connected to the mobile switching center. Now, let us put a customer, a mobile station, a car with a mobile phone in one of the cells, and if this person wishes to establish a call from the mobile phone up to a public switched telephone network, I would like to have a connectivity between the mobile switching center and PSTN, or the public switched telephone network. How the calls happen, what is the anatomy of a phone call, how to initiate a call from a mobile station to a landline phone or from a landline phone to a mobile phone, we will talk about these later. The other thing that I mentioned is, suppose my user is truly mobile, he loves to talk while driving, we should be able to provide some kind of a handoff as the mobile station moves from one cell to the other. What are the good strategies? Again, we have to discuss these features. This slide gives you an overall picture of the cellular telephone systems. Remember, this is a very simplistic model. In reality, cells are neither hexagonal nor equal in shape nor non-overlapping. Please note, the biggest flaw in this diagram is no cell is overlapping, right. In reality, all the cells have a fair amount of overlap. Now, talking about establishing a call from the mobile to the base station and from the base station to the mobile, we make use of channels. Most likely these channels are frequency bands or time slots or codes. So, the forward voice channel is used for voice transmission from the base station to the mobile station. The reverse voice channel is used for voice transmission from the mobile station to the base station. However, as we know, voice channel can be only activated once the handshaking has been done. So, we require some kind of control channel. A forward control channel is used for initiating a call from the base station to the mobile station. A reverse control channel is used to initiate a call from the mobile station to the base station. Please remember, the FCC and the RCC, the control channels, are also called setup channels because of the nature of work they do. Needless to say, the control channels are not used for sending voice, but are used as overheads. They will take a percentage of the bandwidth, typically 5%. In this slide, let us look at the anatomy of a cellular call. A cell phone, when turned on but not engaged in a call, scans the group of forward control channels to determine the one with the strongest signal. Please note, even though you are not making a call, you are using up battery power. Therefore, when you buy a phone, you have two kinds of time available, the talk time and the standby time, right. So, your phone can get discharged over several days even though you do not make a single call, because it has to monitor and keep itself updated as to which cell it is talking to. Therefore, even though you don't touch the phone, the display as to which base station it is connected to may change. It is continuously monitoring the signal strength and knows at any time at least one, if not more, base stations with which it can communicate. So, the mobile phone monitors the channel and keeps on monitoring, because if the strength drops below a certain threshold, it scans for the next strongest. Control channels are defined and standardized throughout the service area. Typically, the control channels use up to 5% of the total number of channels. So, 5% of your resource goes into controlling, setting up your calls. Let us now look at the scenario when you make a call to a mobile user. So, imagine a scenario where a mobile station is somewhere in the geographical area, we have no clue, and we try to make a call to a mobile user. So, we dial this number 98182 XYZ PQ and see what happens. So, the moment you make this call, that is, you dial this number which is pertaining to a mobile, the mobile switching center, which is actually connected to the PSTN, public switched telephone network, provided you are making a call from the landline. Otherwise, from one mobile to another mobile, the mobile switching center must come into the picture. It dispatches the request to all the base stations. Remember, we had connected the mobile switching center to all base stations. Typically, how do we have this connectivity? We can have a fiber, we can have a point to point microwave link, or any other way to connect the mobile switching center to the base stations. So, once the mobile switching center dispatches the request to all the base stations send out a paging message. Now, what is this message? The mobile identification number, which is a characteristic of that mobile station, is being broadcast. It is unique to that mobile. This number may not be the same as the phone number. It is another code. So, mobile station receives the paging message from the base station it is monitoring, because it was already in touch with one base station at least. So, when that particular base station pages it, that is broadcasts this mobile identification number, the mobile station must respond. It responds by identifying it, but over the reverse control channel. Fine. The base station conveys the handshake to the mobile switching center. The mobile switching center instructs the base station to move to an unused voice channel. So, it gives an instruction for the base station to look for an unused voice channel. It may be possible that that particular base station has run out of all the available voice channels. At that time, there will not be the initiation of a call. Question?
Sir, you mentioned that mobile identification number and the mobile number are the different thing.
Yes.
So, where actually the mobile identification number is stored? On the mobile itself or on the base station?
No, this is actually set up in a lookup table inside the mobile switching center. So, there is a lookup table which has the phone numbers and these identification numbers. There is a host of other identification numbers also, which can be used to ensure that legal calls are made. So, for example, in GSM, there is a provision that you can deactivate or label a phone as a stolen phone. So, no phone call can be made from that phone which is labeled as a stolen phone, because that number is blacklisted. Now, what number will be blacklisted? Most likely that MIN will be blacklisted. Alright. So, it stays with the mobile switching center. Then there is something called as a location register. When we talk about GSM phones and basic protocols, we look at the home location register and the visitor location register, where we will keep a lot of information about the mobile phones, including if it is a prepaid card, whether the prepaid money is there, whether it has not defaulted, and what are the call charges. All those details are also kept there. In fact, before a call is established, a lot of things are checked, the validity, the legality and other things. At least there is a provision to check, and only then you initiate a call. Yeah.
So what activities takes place in the handshake phenomenon?
Okay, the question being asked is, what activities takes place in the handshaking phenomenon? So, if you are talking about only the conceptual level, we only verify whether a response has come from the mobile phone, and that mobile phone is a valid phone with a valid SIM card. Okay. We are not talking about the physical layer activity, about the voltage levels or the received signal strength received. Okay. Does that answer your question?
So this mobile identification number is a fixed number for the mobile phone, not the connection, that is SIM card. It is.
That's right. So there are several numbers actually. The SIM card has a number, the handset, the hardware has a number, and then there is a logical phone number. Fine. So it is possible to have a combination of valid numbers.
So this is a hardware number, MIN.
Yes, it's a hardware number. Let's look at a call to a mobile user now. Actually, we are continuing with the call to the mobile user having been paged and responded and being allocated a open frequency band. The base station signals the mobile station to change over to an unused forward voice channel and reverse voice channel. Please remember, both these voice channels have to be available for the call to be initiated. The call has not yet been initiated. We are working on it. Next, a data message called the alert is transmitted over the forward voice channel to instruct the mobile to ring. Mobile so far has not rung. All these sequences of events have occurred just in a couple of seconds and are usually not noticeable to the user. You may hear a series of beeps or a silence period of 3 seconds till you hear the ring. During this process, this figuring out where the mobile is, checking out the identification numbers, allocating of frequency bands, etc. takes place, and then you hear the first ring. While the call is in progress, the mobile switching center adjusts the transmitted power in order to maintain the call quality. So, a lot of intelligence is built into the mobile switching center. However, things have gradually changed, and in the modern base station, a lot of this activity takes place right at the base station. The mobile switching center cannot really handle so much of traffic, and a lot of this thinking part, the power control issues are taken care at the base station itself. As the handsets are becoming more and more microprocessor friendly and powerful microprocessors are being built into handsets, a lot of these power calculations are also done by the handset itself. So, the idea is to distribute the computing so that the mobile switching center is not overloaded. The series of steps I have shown to you belong to the original GSM standard. Let us now look at the other scenario where a call from a mobile user is being made. Remember, at any time the mobile user is already in touch with at least one base station. So, first a call initiation request is sent to the reverse control channel. Remember, the reverse channels are from the mobile to the base station. Along with this, the mobile station transmits its MIN. So, it is in the hardware, but it is also in the table of the mobile switching center. Along with this, another number called the electronic serial number and the phone number of the called party is also set. These different numbers have different utilities in terms of verifications at different levels. Okay. The mobile station also transmits something called as a station class mark SCM, which indicates the maximum transmitted power level to the particular user. Basically, this is a way to control the transmit power. This request is sent to the base station, which forwards the data to the mobile switching center, which in turn validates the data because it has the register locators, it has the database. So, it validates the data, makes the connection to the called party through the public switch telephone network if it is to a landline number or to another mobile. But how to make a call to a mobile is already known to you. We follow that procedure. Again, you may hear a series of beeps or a silence period while all this activity is taking place until you hear the first ring. Okay. Next, we come to a very fundamental concept of frequency reuse. I have already mentioned about it that the spectrum is limited. The only way out is to reuse the spectrum. What is the best way to do it? What is the most efficient way to do it? But before that, let us look at an example to see the true need for frequency reuse. Suppose we had fixed telephone networks and they were running wires to every household. Alright? But we are not talking about wire line truly, we have to compare it to a wireless situation because we are looking at wireless cellular systems. Suppose we would like to give every household in Delhi voice bandwidth. They can talk. So, we need to give about 4 kilohertz of spectrum, but the number of households in Delhi is about 12.5 million. Suppose we get into a stage where we can actually give them 4 kilohertz of bandwidth, we are talking about 50 gigahertz of bandwidth. Clearly, we cannot allow this kind of outrage on a mobile phone network. We do not have the luxury to touch 50 gigahertz of bandwidth. We don't have it. We have to reuse our frequency. So clearly in practical, no other service possible using radio transmission. Most of the spectrum unfortunately will remain unused most of the time. If I give a phone line connection, I cannot do adaptive reallocation. So clearly there is a need to do frequency reuse. This calculation has been done only for voice. If you have to provide additional data, allow them to check their emails over the phone, download stock codes and cricket commentary, we are out of business. Cellular radio systems rely on intelligent allocation and reuse of channels throughout the coverage area. We need to emphasize this point because this forms the crux of the matter. Each base station is allocated a group of radio channels to be used within the small geographic area which you have already defined as a cell. So it's not just a frequency but a frequency band. Neighboring base stations are given different channel allocation from each other because we would like to avoid interference. The biggest problem with frequency reuse is man-made noise or interference. If I am going to reuse the same frequency for transmitting data at a distance, I will definitely get some stray interfering signals, and they're exactly in the same band. You cannot use a filter to filter it out because your data is also in the same band. That also makes a point that I cannot improve my performance by simply increasing the signal to noise ratio. If I increase my signal strength to beat the noise, I'll also create more interference for my friend because the frequency is being reused. Cellular networks must have an efficient power control mechanism. Very important. In fact, your GSM phone monitors the transmit power level 800 times a second. Question? Okay. Now, by the design of antennas and regulating the transmit power, the coverage area within the cell is limited. And the same group of frequencies are reused to cover another cell separated by quote unquote a large enough distance. Why a large enough distance? Because you want to keep this co-channel interference which is generated by cells using the same frequency band under control. Clearly, I would like this co-channel interfering cell to be as far as possible because of the inverse square law that will take place. However, the farther we put the co-channel cell, the less frequently I reuse the frequency, the less capacity I can have. So there is a trade-off between how much capacity I can pack in terms of closely putting the reuse factors, and then we can go ahead and reuse the frequency as and when desired. The design procedure for allocating cells for the cellular base station within a system is called the frequency reuse or frequency planning. Frequency planning should not be very complicated because at the end we have to ensure that certain base stations are using certain bands, the other base stations are using another band, so we cannot really come up with a very complicated scheme. Also, frequency reuse is done in terms of a cluster. So you have a cluster of cells where you reuse the frequency bands and then you replicate that cluster over the entire geographical area. Fine. Let's look at an example of a frequency reuse over a certain geographical area, say Delhi. So here we have an approximate outline of the city of Delhi. You have the neighboring states, you can see the river flowing by, and our job is to set up a frequency reuse pattern in this city of Delhi. So we first start with a cell. Typically a cell will be of a radius of 3 kilometers to 5 kilometers in a city which is urban, and I have put in a hexagonal shape for the sake of clarity only. It is put in blue, indicating a certain frequency band being used. Then I have another cell which is using another frequency band denoted by a separate color, light blue here. It's another hexagonal cell. I am not showing overlap. In reality there will be overlap. So I am going to fill up the space by putting a third cell and another cell and other cell and so on and so forth. So I have put up a cluster of 7 cells here, each one represented by a different color, and each color represents a different frequency band. Clearly the user of adjacent cells are not interfering because they are using different frequency bands and are not going to interfere. I like this cluster and I would like to replicate this cluster all over the geographical area. So I put exactly this cluster of 7 cells nearby. Note that the deep blue one which you started off with is being repeated here, but the distance between this blue and this blue is the same as light green with this light green. So the distance, reuse distance, is the same. Please note that. It is interesting to note that you cannot have any random number of cells in your cluster. I cannot have, for example, a cluster of cells 5 which can have this uniform repeat pattern. We will look at what are the possible cluster size. Let's take this example forward by putting another cluster. Again note that the distance between the green cells, here are the co-channel cells, is the same between this cluster and this cluster, this cluster and this cluster. No frequency band is being discriminated against. All frequency bands are going to suffer through the same co-channel interference levels. So we are excited about this plan, so we put another cluster and another cluster and another cluster, and we are happy that we have been able to cover most of the region by these cells. So this pictorial figure gives where we use what frequency.
So why the distances should be same?
The question being asked is why the distance should be same. The answer is that suppose you take this cell, rotate it and keep it. Then certain cells will have more distance and certain cells will have less distance. Certain group of cells will have poor quality of service because of interference, because distance will attenuate the radiations coming from a co-channel cell. If the distance is fixed and pre-calculated, then we know how much interference we are dealing with. Therefore, I am saying the distance should be same to guarantee a certain level of affordable co-channel interference. If we have this cluster size smaller, say a cluster of 4, then the reuse distance will go down, capacity will go up, and therefore you will have to trade off between the co-channel interference and the reuse distance. So cells with the same color in this diagram reflect same frequencies. In this example, we have used a reuse factor of 1/7. Question?
Sir, over here there is a scenario that each and every cluster has the different type of frequencies. Okay, so now the mobile user will just communicate with the base station. So each and every time they have to change the frequency. Like it will go into the second base station, at that time it will change the frequency. But at the first time when it will talk to the base station, at that time which frequency should be there? Like
Okay.
Is there any common frequency?
The question being asked is, when we switch on a mobile phone or we want to initiate a call, which frequency to choose? Suppose my mobile phone is in this light green cell and it is switched on. It has only a set of frequencies with which it can communicate to this base station. The mobile has a possibility to use any of the frequencies in all the cells, but which particular reverse channel will it use will be dictated by the base station and eventually through the mobile switching center. But the base station in this region would communicate using a frequency band represented by green, and tomorrow if the base station wishes to move to the purple cell or to the orange cell, it will choose the frequency sub-band accordingly.
So that means depending on the channel available, frequencies allocated to the mobile station.
That's right. Depending upon the channels available, the frequencies available and allocated, and suppose a base station can only support the green frequencies while the mobile station moves from the green to the purple cell, a handover will take place not only to the base station but a new channel will be given, which is nothing but a new frequency. Fine. So explicitly I have put arrows to all the light green cells which form the co-channel cells. Similarly, all the purple cells are co-channel cells and will interfere. In the next couple of slides, let's look at the shape of the cells. What determines the shape of the cells? How can we regulate it, if at all? Consider cell I and cell J, which are co-channel cells. Assuming the base station is located at the center of the cell and it's an omnidirectional base station, it radiates circularly in all directions. As we move away, the received strength falls. So just for the sake of this example, let's assume the received power is in dBm with respect to 1 milliwatt. So it's at minus 60 dBm, minus 70 dBm, and so on and so forth as you move away from the cell. Same is the case with cell J. The question is how much you would like to separate the cell so that the received power by cell I coming from cell J is below a certain level. If your handset can handle interferences below 80 but not more than that, I need to decide a certain reuse distance. So who decides the reuse distance? Because the reuse distance can be changed. It can be as low as 1, I don't reuse at all, in the sense that every neighboring cell uses the same frequency, to 3, or change to 4 or 7 or 12. There are certain possible reuse numbers, we will talk about that. Which one to choose for your application depends upon how much interference you can tolerate. Sometimes you can have interference mitigation techniques by signal processing which will allow you to handle larger interference. Then your reuse distance can actually go down. So by signal processing you can make the capacity of the system higher. In reality, the cell shapes would look like this. Why is there a dent here? Possibly there is a building here. Why is there a big dip here? Possibly there is a forest area or foliage which is attenuating the signals. Remember, these contours represent the received signal strength. Note two things. Not only the cells and the received contours are irregular, they are also not equally spaced anymore. In this region, the radiations are going through a medium which is attenuating it differently. Most likely it's going through a concrete jungle here, so that it is falling much faster. So the cell shapes in reality look like this, and these pictures should be taken into consideration to actually decide the reuse distance. Signal strength contours are indicating actual cell coverage. This depends on the terrain, whether it's rocky, foliage, water bodies, presence of obstacles, buildings, towers, and the attenuation in the atmosphere, rain, fog, dust, smog, and other factors. All these factors will determine the received signal strength and hence the shape of the cell. As a system planner, you must consider all these factors before you say, I would like to have a reuse factor of 7. So, let us now see the applicability of the hexagonal cell shape. Why are we using this hexagonal shape? Why is it of importance even academically? So, we have a base station which will radiate. Now, if it is an omnidirectional radiation, then we would have a circular cell. It's ideal. In reality, we would not like to have it for several reasons. But suppose ideal cell of radius 2 to 10 kilometers. Who decides this 2 to 10 kilometer radius? Many features. Of course, it starts with the radiated power and then the other obstacles that may be encountered in the cell. Let us put up one mobile station here and another mobile phone in a car. So, they are very much contained in this circular cell. I would like to do system planning and cover my entire area of interest using circular cells. I can do so, but the problem with putting circular cells for coverage is that you are left with these empty spaces where I cannot predict any coverage. Clearly a bad model. As a mobile system service provider, I must be able to give 99.99% coverage, if not 100%, because my competitor will. I cannot have frequency planning done based on cell shapes which leave out by design some of the areas. So what do I do? I have to try and come up with other cell models which can approximate the circular shape but not leave out sections. So one of the simplest shapes that allow me to cover the entire space by placing cells next to each other is the triangular cell. I can place another triangle cell here, another triangle here, another triangle here. Without leaving up any space, I can cover the entire area of coverage. Clearly, triangle is a poor approximation of a circle. So, in order to maintain close contact with reality, I come up with another cell shape called the square cell. It also has a property to cover the entire geographical region without leaving open spaces. It also approximates the circle, but in a poor manner. In reality, we do not actually use this cell except in certain cases. For example, the LMDS, local to multipoint distribution service, which is based on the IEEE 802.16, which by design uses square cells. But we are not going to discuss that at this moment in time. So, in our quest to come up with a cell shape which approximates the circular ideal shape but is not completely counterintuitive, we go to the next possible shape, which is the hexagonal cell. Clearly, it is closer to the circular ideal shape, right? And it also covers the entire space without leaving blank spaces. Hence, hexagonal cell is used as an approximation to the circular pattern, and that's what we will use, and we'll look at the hexagonal geometry and see how we determine the reuse distance, right? How much co-channel interference we'll get in terms of hexagonal cell pattern. So please remember, hexagonal cells are conceptual. For most theoretical treatment, hexagonal models of cells is adopted because they are a shape that approximates a circle, and using a hexagonal geometry, fewest number of cells can cover the entire geographical region as opposed to a square cell or a triangle cell. So let's stick with hexagonal cells, and you will find it in most textbooks and research papers that they are using hexagonal cells. Next, a few slides on the geometry of hexagons. The regular Cartesian coordinates of x and y, which are orthogonal, are not completely appropriate. So, consider the x-axis and the y-axis, and I have placed a lot of hexagons which are closely spaced. And here, if you look carefully with a slightly darker shade, I have outlined a cluster of 7 cells we had seen earlier. And we have also repeated the cluster so that there is a reuse distance. But we are not comfortable with these hexagonal cells because the moment I go along this x-axis, I sometimes start with a complete cell, then go through it, cut in the middle. I don't like this geometry. What if I look at this axis, which is at a diagonal but touches the centers of each of the hexagons kept in this way, and we put at another axis which touches the centers of all the hexagons along this axis. In that case, we don't have to count fraction amounts of hexagons as we go along any axis. So let us define this funny u-v axis, which are actually separated by 60 degrees. Is the logic clear? We would like to count hexagons. After all, what is a reuse distance? We would like to quantify that number in terms of the cell radius, the side of a hexagon. The beauty is that the distance from the center to any of the corners in the hexagon, if it is r, is the same as the length of a side of the hexagon, which is r. So the cell radius r is the same as the length of a side of a hexagon. I would like to count the distance in terms of the cell radius. How many units are there? How many radii do I move from one cell to other? Fine. So it will be a normalized unit. So if I would like to measure the distance between two co-channel cells D, I want to quote it in terms of this number r. What is r? R is the cell radius, the length of the side of a cell. So the axes u and v intersect at 60 degrees, as we have seen, because hexagons have great affinity to this 60-degree angle. Unit scale is distance between cell centers. Okay. If a cell radius of a point in a hexagon from the distance from the center to one of the corners is r, then 2r cos 30 is 1, or r can be written as 1 over root 3 normalized. And if you do the basic mathematics, you will come to the equation that r is equal to square root of v square plus u square plus uv, coming from simple geometry if you go back. So what it means is we can represent our distance r in terms of units on the uv axis. The uv axis are special because they are separated by 60 degrees. So that equation is written here as the distance is nothing but I units that you move along the u axis, j units that you move along the y axis, v axis. So I squared plus v squared plus uv. Square root of that is the distance. And what happens after this distance? After this distance, you reuse the frequency. So d is the frequency reuse distance, and n is a number which is found by substituting only integer values for I and j, and that tells us after how many cells I reuse the frequency, that is how many cells are in my cluster. because after we run out of the cells in the cluster, we reuse it. From the hexagonal geometry alone, we have that not all integer values of capital N are possible. In fact, if you use integers for I and j, the possible values are 1, 3, 4, 7, 12 and so on and so forth. In fact, if we look at a table for integer values of I and j, we come up with this 1, 3, 7, 12 and so on and so forth. And if you calculate the distance, which is the reuse distance, in terms of the normalized radius, you get a certain figure. This will tell you how far must your co-channel cells be and whether you can tolerate the interference. Let us look at a few quick examples. How to locate a co-channel cell, because co-channel is clearly going to limit the performance of the system. This is your typical 7-cell reuse pattern. You can see 7 cells here, and we have seen this structure before. So I would like to find out after what distance will this cell repeat. Now, for n is equal to 7, using that formula I squared plus j squared plus ij, I is equal to 2 and j is equal to 1 gives you n is equal to 7. 2 squared is 4 plus 1 squared is 5 plus 1 into 2, 2, that gives us 7. So all it means is that if I move 2 units along the I axis and 1 unit along the j axis, I should be able to get a cell which repeats, a co-channel cell that uses the same frequency. So let's translate this cell 2 units along the I axis, which is our favorite u axis, so to say, and 1 unit along the j axis, which is the v axis, and see where we go. So if we go along the y axis, we move 1 unit and we use another unit. So the original cell has now moved 2 units along the I axis. We are only halfway through because we have to move it 1 unit along the v axis, which is at a 60 degree. So let's do that. Along this j axis, let's move it 1 unit. So this original cell has now translated here, and the co-channel cells are actually shown in red. So if you complete the picture, let's put in the cluster, and you see that these 2 cells, which are the co-channel cells, indeed have their own clusters and repeat. N is equal to 7, the cluster size. This logic is true for every cell in the cluster. So I have 7 cells. So take the total band, suppose it is 700 megahertz, you divide it into 100 megahertz each, put each 100 megahertz subband into the cells and repeat it. Let's look at 2 quick examples. This is a cluster size with 12. I have 12 cells in this cluster. If you count carefully, there are 12 cells. And this number n is equal to 12 comes from the same formula I square plus j square plus ij, with I is equal to 2 and j is equal to 2. So in this case, these are the 2 co-channel cells. If you move along the I axis 1 unit and 2 units, and then move along the v axis 1 unit and 2 unit, you get the co-channel cells. Yeah, question?
N is equal to 12 is the number of cells.
N is equal to 12 is the number of cells inside the cluster, and n is equal to 12 has been found by using integer value I is equal to 2 and j is equal to 2 in the formula.
And this whole thing is a cluster.
Yes,
There are 13 things.
yes, because the 13th cell is a reused cell. Fine? Because in the cluster I cannot repeat. Let's look at the next larger cluster size. N is equal to 19. Suppose I have to provide service where my system is extremely sensitive to interference. I cannot reuse frequencies very frequently. I must increase the reuse distance. I'll go to a larger cluster size. Again, for I is equal to 3 and j is equal to 2, you can have these two cluster co-channel cells, and if you move along the I axis, you have 1 unit, 2 units and 3 along I, 1, 2 along the j, again at 60 degrees, and you are with the co-channel cell. Please note, distance here is less than the distance here. This scenario has less interference, clearly this scenario has more interference, much more than the n is equal to 7. In GSM, we use n is equal to 7 and sometimes n is equal to 4, and if I am very ambitious, can also use n is equal to 3. Here we summarize in the sense that I have drawn two clusters for n is equal to 7. You have F1 and then F2, F3, F4, so on and so forth till F7. In the first cluster, I am not using color coding here, and similarly for this second segment. F1 and F1 are co-channel cells separated by something called as a reuse distance from the formula that we have done earlier, and if you substitute in terms of n, r and d, you get the reuse distance d as under root 3n times r, where r is the side of a cell, also the cell radius. Clearly, the distance increases as you increase the cluster size. The reuse factor is defined as d over r. It's a normalized distance with respect to the radius, and it is nothing but under root 3n. Alright, so we'll conclude at this point, and we'll take cell capacity and reuse distances at a next class.